right back, right? So then we have what GPU, graphical processing unit. What is it, graphic processing unit? So they are dedicated hardwares. Initially, they were introduced for improving the graphics, right? Then later, this deep learning people, they are using it for doing some matrix operation and all. That means they are using it as an accelerator. But still, it is a hardware that was pre-configured. Okay, we cannot change the internal what is that configuration. Okay, still we can use it to speed up the application. Okay, and the applications are limited to how the hardware is manufactured. That is GPU. Okay, graphics processing unit. Then we have ASIC, right? So ASIC is application specific integrated circuit. So where we are using ASIC? Suppose you want to you have a deep learning application, a deep learning algorithm, and you want on hardware, and you will use only it for running that particular algorithm. So the entire algorithm can be converted into a hardware. We call it as ASIC. Okay. So the property of ASIC is it is not flexible. That means it's used for one application. Okay. Already it is configured, right? Hardware configuration is done. Then we have fourth type called FPGA, field programmable gate array. So these are hardwares where we can use it for studying algorithm. What are the properties of algorithm? How much resource it is taking. Okay. So in research and academia, we can use this hardware. Why? Because it is not pre-configured. Okay. It has all the hardware units. That means it has logic elements like flip-flop, multiplexers, connection, interconnection. The thing is, it has all the hardware units, but it is not interconnected. What does it mean? Whatever the algorithm you want, we can make the algorithm as a hardware. In future, if you want to implement something else, you can reconfigure it. You can change the connection and a new hardware will be formed. So what is the advantage? It is flexible. Okay. And also it is much more faster than CPU because it has so many resources, so that when I implement an algorithm, parallelism will be huge. Okay. So these things doesn't work on fetch and execute. Only here CPU, our central processing unit, CPU work as fetch and execute. All the other hardwares doesn't work on fetch and execute. We just implement an algorithm in the hardware execute parallel, everything execute in parallel. Okay. But the property of CPU is it is highly flexible. We can execute anything in CPU. But all the other hardwares, flexibility decreases. It is shown in the second figure. Okay, flexibility increases towards CPU, but it decreases towards ASIC. Okay, but the efficiency, the most efficient hardware will be ASIC, application specific integrated circuit. Why so? Even FPGA, more than FPGA, it is more efficient. Why? Because in FPGA, we can interconnect things. But how we interconnect, that depends on the efficiency. Also, the hardware parts are like aligned in a particular way. We cannot interconnect so that the data will move from one place to another place that much fast. But ASIC means for one particular application, I'm building the software. So I can keep certain, suppose memory near my adder. Okay, keep certain memory location inside my near my computational unit. So we can make it faster. That's why ASIC is more faster than FPGA. Okay. And so I'll be focusing on FPGA based hardware implementation, because that's what we are going to use in academia and for research. Okay. For ECE background people, they will actually use FPGA for testing their circuit. Then later they will go for IC designing. Okay. So FPGA can be used for testing that I will tell what are the uses of FPGA. Okay. So where we can find FPGA? Nowadays, FPGAs can be found in anywhere, from aerospace till IoT devices, we can find FPGA devices. Okay. So aerospace means in order to, in certain applications, the algorithm will keep on changing, or some security parameters will keep on changing. Okay, if we are implementing FPGA in that case, what will happen is we can change the configuration so quickly that that security parameters can be incorporated within seconds. So if an attack happens to a particular organization or something, and they are using a hardware for updating the solution, if I am using FPGA, I can correct it so quickly because FPGA is reconfigurable. Okay, so FPGA, you can see aerospace application, automotive, high performance computing like in servers and all, even IoT devices also you can see. IoT devices are very small devices, right? So what they have done is recently they have created one small FPGA chip that you can see it in the right hand side. On device I have kept, that is the SoC for, that is the latest SoC for IoT. SoC, what is SoC and FPGA? SoC is also an FPGA. SoC means system on chip. SoC means it will contain a small processor and an FPGA part. Small processor and an FPGA part. Okay, in mobile phones. Okay, nowadays these iPhones are using FPGA, SoC. I think you might have read about it, right? AI SoC, they have kept it. Okay, so it will contain a processor. Mostly it will be an ARM processor and a small FPGA part. Okay, then FPGA, now machine learning is growing fast, machine learning, deep learning. So in that case, we don't want to use our CPU for executing deep learning algorithm, right? It will take lot of time. Okay, so in that case also we can go for FPGA. Okay, FPGA as an accelerator. Accelerator means increasing the speed, right? Accelerate my process. Okay, so how for which application we were using FPGA? Just to one overall view. So FPGA, we are hearing it everywhere nowadays. Actually, initially FPGAs were used for prototyping. If you want to manufacture a chip, okay, so we will not directly go for chip manufacturing. First, we will test it in FPGA, whether the circuit will work or not. If everything is okay, we'll go for IC manufacturing. So initial days in 1980s and all, we were using it for that purpose. And for glue logic. Glue logic means connecting our system with the peripherals and all. Okay. Then later we started using it for digital signal processing, network communication. From 2000 onwards, we are using FPGA for high performance embedded system, then SDN, software defined network, AI and IoT. Okay. So FPGA is having this much importance. That's why I was telling. So if you are going to learn some hardware implementation, you should choose FPGA. Okay. Because even computer science students also now you can learn how to design a hardware using FPGA, because they have introduced the C-based, CPP-based, Python-based software for creating hardware. Okay. So I'll just share an overview of FPGA. What is FPGA? Okay, just quickly on tour. Okay, so FPGA is also an integrated circuit. Okay, the only thing is can be programmed and reprogrammed with a different logic. Okay, so I will show with a figure. So the left-hand side shows the picture of overall view of an FPGA. It contains logic blocks. These yellow color blocks are called logic blocks or CLB, configurable logic block, configuration logic block. Okay, each this yellow color block contains the right-hand side things. LUT. LUT means lookup table. It will be used for implementing logic. Okay, then flip-flop, multiplexers. Okay, so each of these CLB will contain a set of these logic block. Okay, then we have we will be implementing our logic in this yellow color block. If I want to connect two blocks, we have interconnects in between the lines. Okay, programmable interconnect. You can connect in whichever way you want. Okay, so after suppose I have implemented one algorithm inside my FPGA. Now I want to give input and take output. For that, I have input output block around all these CLBs. Okay, you can connect USB, Ethernet, PCIe. Okay, PCIe is very fast interconnect. Okay. So then what is the difference between how does the program execute in CPU and FPGA? I have shown here two figures. Okay, the left hand side is, this is a C code and it is used for A plus, B plus, C plus, T plus, E up to H. Okay, so usually how ALU will work, instruction by instruction, it will fetch and execute it, right? And in FPGA, in right hand side, you can see how it is executed. Actually, A plus B, for A plus B, I'll create a logic inside FPGA. C plus D on logic, E plus F on logic. Logic means on adder I will keep that. Okay. Then A, B, C, and D, etc. that I can keep it inside a small memory. LUT can be used as a memory, or some other memories are also available like VRAM. Okay. So this will be created inside FPGA. So what will happen is within one clock cycle, I can complete this, the whole operation inside FPGA. But ALU will take so many clock cycles, depends on its speed. Okay. So this is the difference between a code that is being executed inside a CPU and inside a FPGA. Okay. I hope you got the point. So that's how we are getting high level of parallelism inside FPGA. We are using more resources from FPGA. Okay. So how does the FPGA work? First of all, the configuration, mapping, execution. Configuration is nothing but we have to write the code for our program. Okay, suppose you want to write, execute a deep learning algorithm. Write the code in Verilog hardware language, Verilog, VHDL, or nowadays we can write it in CCPP, OpenCL also. Python also nowadays is available. Okay. So this will be mapped to FPGA components. We don't have to map it. The software will map it. You have to just give this input, Verilog, VHDL code, or C or CPP. Okay. Then mapping means the software will do the mapping. Okay. Will convert it into some internal format and it will map to CLB. I mean, how many flip-flop, how many LUTs, how many multiplexers required, it will, everything the software will take care. Then after that, what we will do, execution. Okay. The software will give on binary output. Okay. It is called a bit stream. On binary output we will get from software that we can execute inside the FPGA. Okay. This is how to create a hardware inside an FPGA. Okay. So why we are using FPGA, like I already told you, flexible. Flexibility means we can reprogram it again and again. Okay. Performance, high performance, parallelism we can achieve. Then customization. Customization means if I don't want one algorithm, I can go for another algorithm. In the same algorithm itself, if there is a parameter change, I don't have to create a new whole hardware. I can just change a part of the hardware. Okay. Suppose I have an FPGA with a whole algorithm. Okay. In future, I don't want one part. Instead, I want another part that I can do. Okay. That is called a partial reconfiguration. Okay. Then rapid prototyping. Rapid prototyping means I can just do within an hour. If you know how to program, I can do it within an hour or half an hour. Power efficiency. Okay. It takes less power than CPU. This FPGAs run at a lower clock cycle. Okay. 500, 600 megahertz it will run and it will give high parallelism. But our CPUs runs in 2.4, 2.63 gigahertz and all, right? So less power consumption. Then high speed interfaces are available. Like I told, PCIe is also available. Okay. Okay. So we are going to consider the hardware security issues of FPGA design. Okay. So whatever the security issues I'm talking here, it is applicable for other hardware also, like integrated circuits. Okay. So the main hardware issue we are facing are, so vulnerability in FPGA design. Okay. So suppose you have created a design. Okay. So before that, let me tell you one thing. So nowadays your mobile phone is coming from different areas, right? Globalization. With the globalization, what happens actually, each part comes from different parts of the world, and someone will assemble it, and someone from somewhere it comes, right? So what will happen to the hardware? It goes through different hands, right? So there are many security vulnerabilities possible in hardware. Some of them you might have seen in news and all. So they can keep a small circuit inside your mobile phone, okay, that keep on sending your secret key or secret information through a covert channel, right? So this one you cannot find out through software, right? So the same kind of thing happens within FPGA as well. Okay. So if we are considering FPGA, the security issues happens in FPGA design. Design means if you are creating a cryptographic hardware, okay, that design someone will keep a small circuit. Okay, that can happen. Then configuration bit stream. What is the configuration bit stream? Like I told, after design, we will get an output, binary output. That is called a bit stream. Okay, that also can be tampered. Okay. Then side channel attack. What is a side channel attack? I'll cover that in another slide. Side channel attack means if an hardware is executing, okay, some properties of that execution we can capture. For example, how much power each operation is taking. Okay, by calculating that which operation it is, we can find it out. Okay, or if I'm doing an encryption, how much time it is taking for encryption. Based on that, I can guess the bit size, key size. Okay, and different types of side channel I will cover. Okay, then some other are backdoors. What are backdoors? In backdoor means that means in order to get access to a device, okay, an intruder will keep an point. Through there also I will get an access. Okay. Then Trojans means, Trojans, like I told, keeping a small circuit that is undetectable. Okay. Upon giving some trigger, what will happen? It will start doing his functionality. Functionality means maybe your key or maybe your bank account password. It will be leaking from your memory. Okay. So how it will leak from your memory? If I'm using software, it is difficult because we have several software mechanisms to avoid that protection. Okay. If I keep a small chip inside my mobile phone, what will happen? It will have all the access privileges, right? So what will happen? Even the attacker can remotely control the mobile phone, right? It can give, he can get the access privilege to all the things. Okay. Yeah, Trojans also can be used as a backdoor. Yeah. Okay, so side channel attack. I'm just which are the types of side channel attacks I'm showing here. So power analysis attack, electromagnetic attack, timing analysis. Okay, like the name shows, what is the power analysis attack? So power analysis means for each operation, it will take a certain amount of power, right? So by analyzing the power, the attacker can guess which operation it is or what is the key length and all. So how can we counter? So some researchers have given some solution for power analysis attack. Like we will introduce some more. So power analysis attack, how we can overcome is all the operation, we will keep it as same power by adding same number of resources. Okay, even some more resources we will have to introduce, but the advantage is all the operation has same amount of resources, like a gate, number of flip-flop. So it will take the same power. So an attacker cannot analyze how much less or how much more power it is taking. That is one kind of counter attack. Okay. So electromagnetic attacks also same. Based on how much electromagnetic emission a particular device is producing, based on that, he will try to analyze the important information. Timing attack, like I told, how much time a particular operation taking. Okay, based on that, because all the operation take different type of amount of time. It will have multiplexers, adders. Multiplexer take different amount of time. Adders take different amount of time. Okay, there also what we can do is we can add some dummy circuit or make all the timing same. Okay. So next type of attack is reverse engineering. Have you heard about it? Reverse engineering. What is reverse engineering and why is it important? So you have your iPhone, right? So do you know an iPhone cost 3,000 rupees? You will get it. So reverse engineering means what they will do is they will get a legitimate device. Okay, they will find out the internal working, which are the parts available. They will find out everything. Then they will remanufacture it. Remanufacturing with low price materials. Okay, same thing, but with low price material. And what will they gain? A large amount of gain they will get, right? Money. Okay, so reverse engineering. Okay. Okay, so both our integrated circuit and FPGA design, both are vulnerable to reverse engineering attack. Okay. So what is the solution for reverse engineering? In order to avoid reverse engineering, I will tell you one method. If reverse engineering has happened, you got a device, how will you know whether it is original or duplicate? Nowadays, everything you will get duplicate, right? Everything, even laptop also online, you will get duplicate things. How will you know? The one solution researchers has told us, we will make a stamp on all the original devices. Stamp means it is called watermarking. Okay, that is one method. So that whether if there is a stamp in the particular hardware, it is not a physical stamp, it is something logical thing. Okay, if it is there, then we can tell that it is a legitimate one. Okay, then some other puff. Okay, now in order to avoid reverse engineering, how to avoid reverse engineering? Okay, that I will discuss in the next slide. Before that, one more attack I'll tell. Insertion of Trojans and other things. So malicious insertion comes in three forms mainly: Trojans, backdoors, malware. Okay. So Trojans, you know, what are the difference between these three? Trojans means some circuit they will introduce. Okay, it will be dormant, it will not work. Whenever the attacker wants to steal some information or malfunction the circuit, they will activate the circuit by giving a trigger. Okay, in World War II also something happened. They have introduced a small circuit. So instead of giving one particular order, they have given the order like attack or something. Okay, so that Trojan insertion is, even our mobile phone will have small Trojans. Okay, can have, I'm not telling will have, can have. So an attacker will get an unauthorized access or intentional malfunction. It will show like it is doing one thing, but it will be doing another thing, like leaking information or something. Okay, then backdoors also, they are also malicious insertion. So they are hidden access points. Okay, usually if I am getting a device, only a particular authorized person can access it. Okay, backdoor means whoever is designing or whoever after the design phase, they will just give an access point. Using that access point, I can get all the access into the device. Okay, and it can bypass the normal security mechanism. You don't have to enter the password or your fingerprint or anything. You can directly access by giving a small code or something. Okay, then malware or malicious code. Okay, So if I am introducing a malware in a hardware, what I can do? I can get the remote access through to the device and sabotage the entire device. Okay, that is also a malicious insertion. Okay, so so I have told about some of the attacks. In which phase of my FPGA design or FPGA creation this attack can happen? So whenever an FPGA device is being designed, this attack can happen. FPGA fabrication, FPGA assembly, or FPGA design. We people usually go for, will do only FPGA design. These are all the FPGA manufacturing phases. Okay, in all these cases, it is open to different types of attack. All these attacks, I have shown here only Trojan horse. All of these attacks are possible. All the hardware attacks are possible. Okay. So which are the methods we can use in order to provide intellectual, what is an intellectual property IP in a FPGA design? An example, I can tell a simple example. You are using an encryption algorithm. For example, nowadays you all are using AES. Okay. So I want to use AES in my system, but I don't know how to write the code. So someone will write the code. Okay. And it is their intellectual property. They have written the code and gave me as a module. Okay. That I can use it inside my hardware design. Okay. That I will call it as intellectual property. Okay. I can design it. It can come from third party, or it will be inside already inbuilt repository. Okay. Repository means if I am using a software for designing a hardware, it has some components, modules. Okay. Those are all, maybe silence people, company people have designed it and kept it. That also IP. Okay. So how can I protect an IP? Okay. IP is the most important thing to be protected. Okay. Because encryption module I'm using it for encrypting the data. That is the main thing. All the other interconnections are not that much important. Okay. So how we will protect? Through encryption. First of all, through encryption. Encryption of what? Here we are dealing with the hardware, not software. While coming to software, encryption means encryption of data. While coming to hardware, how encryption? Encryption of bit stream. I told you, right? FPGA give output as a binary file. That binary file represents a hardware. Okay, hardware logic. So encrypting that bit stream means one method. Okay, and recently researchers have shown that encryption is not a safe method for encrypting the bit stream. Encryption is useful for encrypting digital data, our data, plain data, not for encrypting this bit stream, because it will show some similarity. Okay. Some papers are published showing how vulnerable this encryption is. Okay. Then secure configuration, like a secure boot mechanism or authentication protocol. While booting, we use some protocols, right? We can follow that. Then IP core protection, protect the IP core by encrypting or by obfuscating. I will tell about this obfuscation later. Okay. Then logic locking. Okay, so this is the logic locking. I'll come back. Then watermarking. What is the watermarking? Watermarking is used to identify a legitimate hardware part. Like I told you, if I'm buying one particular hardware from one person or a particular IP from a person, he will authenticate it by keeping a watermark. If the watermark is there, it is an authenticated one. Okay, I can use that method. Then secure supply chain. Secure supply chain means if I'm creating a hardware or a FPGA design, all the parts should come from an authorized dealer. The dealer should be trustworthy. Supply chain means that process. Okay, designing, manufacturing, those processes called as supply chain. Access control, using some software, we can give access control. Username, password, something like that. Then what is this logic locking? It is a currently evolving topic, this logic locking in security. So, encryption is used for encrypting the data. Logic locking is for encrypting the circuit. Okay. I'll just tell about it because it is very important. What is logic locking? Okay. So usually logic locking means I have an input circuit. Okay. I'll give to logic locking and I will get a logged circuit, not encrypted circuit, a logged circuit. In order to decrypt it, the logged circuit will be given to a decryptor. I will get an unlocked circuit. What is this locking and unlocking? In the next slide, I have explained it. Suppose this is my digital circuit. Okay, locking means I will insert some additional gates. Here I have shown only XOR. You can use anything. Okay, XOR or OR gate, AND gate, multiplexers or anything. I will add some gates in between this logic circuit. And one input to that gate will be from the input from the previous gate. And another bit will be key bit. That means if this circuit has to work, I have to give this K1, K2, K3. This key bit I should give properly. Okay, this is called a logic locking. Okay, the simple one, I have a logic circuit. I logged it by inserting some additional gates. Those additional gates are controlled by external bits. Those bits are called key bits. If I provide this key bits properly, the actual key, the circuit will work. Okay, so this is called the locking of digital circuit. Okay, logic locking or logic encryption. Okay, so this makes sense better than using our usual encryption process for encrypting the circuit. That is not logical, right? So in order to encrypt the circuit, we should go for hardware locking itself. Okay, so this is one currently evolving topic in integrated circuit as well as FPGA design security. Okay, so if you want to implement this kind of logic locking, what do you need to learn first? First of all, you have to learn how to design a hardware, right? You have an algorithm, you have to map it to a hardware or create hardware for your algorithm, then go for locking. Okay, so with this kind of locking, which are all attack we can eliminate? No, not predefined. It depends on how big it is and the trade-off between performance and security. If I add too many gates to the circuit, the performance will decrease. And if it is in the main line, that is the designer, whoever is designing the circuit, whoever is locking the circuit, designer, hardware designer.
Believing the designer, then why you
Not believing the means, see, here we are assuming that I am going to trust the designer. Okay, otherwise we cannot trust anything, right? So designer is designing the hardware. The designer will give it to a foundry, okay, for manufacturing. In between the foundry, testing will happen, verification. In testing phase, someone can insert the thing, right? So if designer itself is a unauthorized person, then this won't work. Okay, so that's why we have to go for authorized dealers for the basic parts. Almost all the manufacturing companies, they all go to the authorized dealers only. Okay. Otherwise, surely something they will introduce. If you are going to an unauthorized party, they will have some connection to other people. Surely something will happen, right? So, regarding number of gates, number of performance, based on performance and the security, we have to control number of gates to be inserted. If I add too many gates, performance will decrease. If I add a very less number of gates, what will happen? Security will decrease. Because brute force attack is possible. Several attacks are possible in this scheme. Okay. So I will just introduce two methods that is published in 2008 and 2015. These are the two basic ones. The first one is random logic encryption. Logic encryption or logic locking. Okay. So this is the first paper that was published by Roy et al. Okay. So it was like they have introduced logic encryption, like just randomly insert the key gates anywhere. That was their method. Randomly insert somewhere. Okay. Then number of key gates, they were decided based on the performance and security trade-off, how much performance they need. Based on that, they have decided. But the thing is, it is prone to many attacks. If the attacker knows the key gates, he can find out the key bits just by trying all the key bits. Okay, because the thing is, we will insert one logic gate in one place, another in some other place. Though those two are not interconnected, then brute force attack is very easy. That's why. Okay. Then second method, by avoiding some attacks, they have introduced fault analysis based LE. Fault analysis means if I am inserting some additional gates inside my circuit, how much fault it is giving to the output. Based on that, I will insert my key gates. The position and the number of key gates will be decided by how much fault it is producing in the output with the wrong key. Okay, with the wrong key. With the right key? Yeah, I'm not getting, sir. Fault, there are many methods. See, fault based means I know my output. I'm the designer, I know my output. If I'm inserting the key gates, output will change. How much fault it is? Yeah, that's what I was talking, sir. Randomly means randomly I'm assigning. I'm not checking any input or output. That's what I was talking about initially, right? Randomly, I'm not checking any input or output. Randomly, just random. That's the name. Okay. So fault means I'm analyzing something, then inserting my key gates. Okay. So anything else, sir? It's nothing is predefined here, sir. This is on risk. I'm not getting, sir. The left one is randomly. That is one method. The second one is next method. Someone has to design, right, sir? So designer will decide. Yes, designer. Yes, he knows the correct one as well as the faulty one. He will check the both output. See, that's how the cryptographic gear area works, right? So if I want to check the diffusion, confusion, and what we will do? What we will do, sir? Same thing. We will analyze the difference between both original and the faulty one. Okay. So the next one. So the next topic, what I want to talk about is, so how to create a hardware in an FPGA. Okay. So after learning this only, you will be able to implement any security mechanisms in hardware. Okay. So I'll just talk about cryptographic accelerators in FPGA. What are called cryptographic accelerators, or in general accelerator? I told you initially, accelerator means accelerate the process, speed up the process. You can use the accelerator for accelerating any algorithm. Nowadays, you will be focusing on deep learning, right? ML algorithm. You can implement it in FPGA. Okay. Previously, we were using it for cryptography. Cryptographic accelerators are used in many situations in cloud servers and all. We have several encryption, decryption going on, right? There, they don't use CPU time. There, they always use FPGA in cloud servers. Okay, because encryption, decryption happens all the time. We cannot depend on CPU. Okay. So the role of accelerators are performance. We can, there we don't have FPGA. There we can use ASIC. ASIC is more, much more faster than FPGA. If you know the process in prior, if this is the process I have to do, then you can go for ASIC, because ASIC is much more faster than FPGA. Okay. So in blockchain and all, if you know the process, you can go for ASIC. That is better. Okay. Because ASIC is more faster than FPGA. Okay. Then hardware level security we can give. So the next point is protected key storage, tamper resistance design, and physical security mechanism. So all these things. So whenever someone is creating a hardware, they don't keep security in mind. They just focus on performance. Everywhere security is an add-on feature, right? So if an researcher is or a person who is interested in security, they can use FPGA for creating the hardware security. That is much more easier. Okay. Instead of going for building an integrated circuit. Okay. So then low latency and deterministic timing, these are all I have told you. Power efficiency, the reason I have told you why the power efficiency is coming. Then flexible algorithm support. Okay. If there is any change in the algorithm, we can change it quickly in using FPGA. We have to just reconfigure it. For that, one method is the dynamic partial reconfiguration. Okay. Resource optimization we can do. How much resource? These all things we can do it in software. If you know more about hardware languages like Verilog and VSTL, you can do more of resource optimization. If you're a software engineer, you can do everything in software, but that has a limit. Okay. Design flexibility reconfiguration, like I told you. Okay. I'll just explain this figure using this. Both are same actually. So how we are using an accelerator actually, or how we are creating a hardware for an algorithm. We have a core, CPU core should be there. For example, a small CPU should be there. You can use ARM Cortex, say this one processor you can use. Most of the SoC will contain ARM Cortex. Okay. So in general, I am calling it as CPU core. Okay. For what purpose, I will tell you. So one part will contain a processor, another part will contain an FPGA. Okay. I was talking about FPGA is used as accelerator. Why I am using a CPU alongside with it? Because I have to control the whatever it is inside. I have to give the input, collect input, present to the outside world. Those things we can give to CPU, because those things, if I go for FPGA, it will take more resources. Those things I can go for CPU. Okay. So in giving input, collecting input, show it to the user. Okay. Interfacing we can do. And in the right-hand side, I have shown you FPGA part. There I will create some cryptographic unit. Okay, since I'm talking about security, I'm talking about cryptographic unit. Any algorithm you can implement there. So I will show a case study here, and I will try to show a demo. Okay, so are you familiar with encryption? Fourth semester students, you are not familiar with encryption, right? Okay, I'll just assume that this is an algorithm that is used for encryption. Okay, that is 120. This is 128-bit AES. It will take the input, do some operation, and we will get the output. Okay. So these are the steps we usually follow for AES encryption: add round key, substitute by, shift rows, mix column, key expansion. Okay. What I want is, if you are doing in a computer system, usually you execute inside a CPU. What I want is, I want to create a hardware for this algorithm. Okay. So how we can do it? Okay. So there are many companies that manufacture FPGA. Xilinx is one among them. Okay. Xilinx manufactures FPGA, and also software we will get. Okay. So I'll introduce you to 3 softwares: Xilinx HLS, high level synthesis; Xilinx Vivado; then Xilinx SDK, software design kit, last one. Okay. So first one, Xilinx HLS, high level synthesis. As the name implies, what we will do is, we will write our algorithm in high level language like C, CPP, or OpenCL. Nowadays, Python is also there. I will write it in HLS. Okay. HLS will automatically convert it into Verilog. Okay, that means it will create one package. It will contain Verilog code. Okay, that package, in other words, we will call it as IP. Okay, IP, I will give it to Vivado. Inside Vivado, I will do the hardware designing. It's easy. The software will do almost all the thing. If you are a software engineer, if you are a electronic students, then you can do it in Verilog also. For software engineering, software will do everything. I'll show it. Okay. Then Xilinx SDK, software design kit. Why I'm using a third software? I have designed hardware here itself in Vivado in second one. The third one is for giving the input to my IP or hardware, collecting input and showing it to user. That's all. That means interfacing to the hardware, the third one. Okay. Third one, interfacing my software to hardware. That's why this third one. Okay. And I will show. So this is the FPGA or SoC, system on chip or FPGA. Okay. So it will contain two processors. Usually depends on the board. Okay. Some board will not have this processor. Some board will have this processor. Okay. So these are two processors showing. One cache is there. Memory controller is there. This is called the PS part, processor system. That means I can't change this part. This is hard. Okay. Then right hand side is my FPGA part, PL, programmable logic. Okay. So it contains all the all the components like logic gates, multiplexes, which are not interconnected. Here where I'm going to use my my custom hardware. Okay. So I can connect this part and this part through some interface. Okay. AXI interconnect is there, advanceable extensive interconnect. AXI interface is available. Electronic students, they might know it. Okay, you don't have to go that much deep. Okay, so this is the FPGA design flow. First of all, we will create IP. That means I want to create a cryptographic hardware. Okay, I will create, first of all, I will write the C code here. Then design phase, simulation phase, synthesis, implementation, bitstream generation, then application development. Each of these phases has different functionality. IP creation done, writing the code in some language. Then system design means after writing the code, I have to attach to the PS part. Then only I can interconnect. I can read and write from to and from the FPGA. Then simulation. Why we are doing simulation? We have to check the functionality of my hardware, right? I have done C code. Okay. Verilog is converted to Verilog. I have to check whether it will work or not. Functional verification and all, I can do it in simulation. Using some waveforms we can see. Then synthesis. Synthesis will convert the simulated output to some RTL form, register transfer form. That means I can get the output from the synthesis as logic components in AND gate, OR gate, what you have written in C language. If I want to see it in AND gate, OR gate, multiplexes, I will get after synthesis. Synthesis will convert my code into logic design. Okay. Then after synthesis, implementation. Implementation means I got my logic gates, everything. Now I want to implement it in actual FPGA resource. That will be done in implementation. Okay, how many LUTs required, which are they, how to interconnect them, that will be done here. Then bitstream generation means the output bit file binary generation. Okay, binary file. Then at last application development in order to give input and get the output in. Okay, application development means I'll develop an application to give input by accelerator and get from there, output from there. This is the accelerator process. It's not parts. It's the process, how to design an accelerator. In order to design an accelerator, I need both PS part and PL part. Board, no, sir, like I told you, that's why I'm telling you, a board will contain both part. Okay. If a board, some of the board doesn't have the left part, but they still have a soft core, that you have to read. Okay, those are additional details. Okay, some board will not have this hardware ARM processor, but there we have soft processor. Soft processor means already they built a processor code. We can just keep it inside PL part. Okay, but when you learn initially, this is the proper way. Okay, so this whole constitute, without the left part, we cannot tell that we are creating an accelerator. Both are necessary. Okay, but my code goes here. That is true. Accelerator code goes here. Okay. That's what we are going to do, sir. Here, design phase. Yes. But this for software developers, this design phase, if you know Verilog properly, designing you can do it using Verilog very clearly. If you don't know, we will go for system generated thing. System will automatically configure everything. Okay, we will go for that. But the problem with the system configuration is there will be some performance, less performance. Okay, that's all. But if someone doesn't know and try to improve performance, that will even degrade from the system automatically. SDK is necessary when you are going to develop an application which we are going to use the accelerator. Application means, suppose you have your system, you want to encrypt it and send it through your email. Okay, so you will get a window, right? Yeah. Application development is the SDK part. Application development is the SDK part. Okay, here HLS will be happening in, here IP creation will be happening in HLS. From here to here, it will happen in Vivado. That means from, so I don't have system design till bitstream generation, it will happen in second one, Vivado. Okay, then the last one will happen in SDK. Okay. After that, this is from SDK. See, okay, I got the doubt. So till here you have reached. You have 3 softwares in your system. Okay, shall I show you in the demo? That time you will understand. Okay, after SDK, I will use my board, connect it, program it. Okay, I'll show it in my, so I will just to show the demo. Actually, I have written one previous code. I'll open it. Okay, I'm not going to execute it because it is an old software. It won't execute now. Okay, this is a pre-compiled one. So here I have written C code for AES. Okay, here you can execute it by clicking this button. I cannot see. Okay, here, this one. Okay, this button. So now I am not clicking because it won't work now. I'll just, okay. If I click it here, it will try execute this one. If there is any error, it will show error. Okay. Okay. Then there is one you can see one box here, right? Export RTL. I'm just telling only the necessary things. In order to learn this, you will have to spend some time. The software is really big actually. I'm just telling only the necessary things. Okay. So I have written the C code. I'll execute it. Here I can see whether if there is any error. If there is no error, the window will come here. It will show here. It will show how much latency it will take. It is not the original one. This is just a simulation, how much flip-flop and all it is taking. Okay. It will show this is just a simulation HLS. This is not the actual implementation. So these things are not real. This is just an estimation. Okay. I will show the real in the next one. Then here one box you can see. Okay. This box means I will convert my C code into Verilog and create an IP. Okay. When I click this box, okay, one IP will be created, but nothing will be shown here. The output will come here like successful, come here in console. Okay. I won't see anything. Okay. Fine. Here it will execute. It will show success. This box means I will convert it into Verilog, not I. The system will convert it into Verilog and an IP will be created. Okay. Now I will go to the next software, Vivado. Okay. You have to create a new project here. Okay. I have already created one project. Why I am not executing is problem with licensing. Okay. So I have already created one. I'm opening that. Okay. So here, if you go, okay. So here, what I have done is, this is the IP I have created from there that I will show that may work. Okay. So where we reached till here, we have reached, right? We have executed, packed as an IP. Now an IP is created in this, in whichever it is saved, location is saved. Okay. Now I'll come here. Okay. Suppose nothing is there. This is blank. It will be blank initially. So what I will do is I'll go to project setting, IP. Okay. Okay. Inside that, I have one tab called package or general repository manager. Okay. So I can, so what I have done here, I have created on IP. Okay. Like I told here, I have created on IP. Only first step I have done. Okay. Second step, what I have to do is I have to take that IP inside here. What I will do is I will click add button. Okay. So wherever I have saved this project. Okay. This project I saved in D, Vivado demo AES. Okay. That folder I have to select here. Okay. Inside D, Vivado AES, I will select. Okay. So already I have imported. That's why an error is showing. Imported. Okay. That means I have imported the IP I have created in the other software. Click OK. Apply and OK. Okay. Fine. Now what I will do is, here there is one plus sign. This software also, in order to learn it, it will take, I don't know, maybe 1 month it will take. Okay. So I'll just introduce you the main thing. So here it was blank initially. Okay. I want to do the next step, system design. Okay. So what I will do is, system design means what are all the parts there in system? Check it. There is a PS part. There is a PL part. I want to do the interconnection. I didn't do the PS part. Okay. So PS part, in order to do the interconnection, I have to add the PS here, processing system. For that, there is a small button here, add IP. All the IP created by Xilinx company will be here. Okay. That may come from Xilinx, or maybe they bought from some third party. Okay. So here, if I type ZYNQ, I will get this one. I'll double click it. Okay. The same thing, it will insert here. See? Okay. I'll do one thing. I'll just delete everything and I'll check it. Maybe it will work. Okay. Okay, sync. So this is the first thing you have to add. And it is telling that run automation. Some internal connection need to be done. Let the software do it. Okay, you can customize it actually. It will take some time. That means it has so many interconnects actually. We don't need everything. Okay, so you can customize it by clicking that one. Now you don't have to do it. Just to give the default one. Okay, so this is the processing system. Now what I want is I want my AES-IP. Okay, AES, if I type, it will come here. See, if I don't add that in IP catalog, it won't come here. Okay, so project settings here I have added from external source. That's how it came. Okay, came here. Not connected. You can connect manually if you are very much familiar with the hardware connection, or let the system do it. Run connection automation. Okay. Okay. So what happens is I have created one AES IP. Okay. This is just a design. Nothing happened. Okay. The second phase. Design. Okay. Now here I can do simulation, synthesis, implementation, bitstream generation. If I give bitstream generation directly, it will do everything else. If you know how to see the output in waveform, you can do it in run simulation. I'm not going to execute it. This software will not work. Okay. So you can do everything. Okay. Then one more thing. If you want to test the functionality, how will you do? Two ways are there. You can do here. Here, if you are doing, you have to write the code in Verilog. In Vivado, you must write in Verilog. You cannot write C. Okay. If you want to write it in C, you can do it here. The other one, HLS. Okay. Okay. Here, in order to check the simulation, you have to give it in Verilog file. Okay. That you have to give it in here, simulation sources. That I'm not doing now. Then you can go for synthesis, implementation, bitstream generation. Verilog file you will see here. Where is it? You can see here as well also. Here is the Verilog file. Here also you can see. And in HLS also you'll be able to see. Here inside synthesis, I have created the Verilog file. Here also you can see AES.v. Okay. And all the modules have come here. AES expand key, add round the key. Main modules, it will come as different modules. Okay. Better not to touch any Verilog file if you don't know Verilog. Keep it like that. Okay. So I have generated bitstream here. Okay, so we have done from synthesis design, simulation, system design, simulation, synthesis, implementation, bitstream generation. Everything system will take care. Okay. Even here also, if you know Verilog, you can do implementation by yourself by allocating the resources properly using Verilog code. Everything you can do yourself if you know Verilog. If you're a software engineer, let the system do it. Okay. After the bitstream generation, we have to open the SDK. So for that, what I have to do is I have to do file. I have to first step is export hardware. I have already exported. I think it will. You have to do export hardware. Okay. File, export hardware. Just some lines of code it will show. Okay. That's all. Nothing it will show. After that, launch SDK. Next line, launch SDK. Click OK. Yes. Okay. So here, I'll close all the things. I have opened it previously. That's why it is showing some files. Here, we are going to develop an application, new application. Okay, any application name you can give. Next. And it depends on your application, you can select. If you are an initial user, you can go for Hello World. Just an application. Okay. And that is used for many different hardware and okay. So here we can write C code. Okay. And you can access the hardware. The platform is the cryptographic hardware we have created, right? It came here. Okay. So you will get all those things, platform configuration, .h, .c. Then some other, those are there. Where are they? Not verified. Here, PSP. These things, if you want to, you have to learn these things actually. How to program it, how to develop the application. Okay. The thing is, all the, I will tell you one thing, how to develop the SDK application. So here we have reached till here, right? So I have a hardware accelerator now. Now what I want is I have to give input to it and get output. Okay. So the connection has been established already. Connection means this connection has been established. Okay, but we don't know how to do it. So the thing is, SDK will automatically, it will provide some functions so that we can write and read to and from the hardware. Okay, so those functions you can find it here. Here, this someplace here. Just to go through here something will be there. So here include. So all these header files will contain the function name. xaes.h, there is one file. Okay, inside that we have all the functions we need. Key in. Key means what is key? While designing the algorithm, I have given one input as key. Okay, so all these functions, we can use it inside my C program to create the application. Okay. So in order to, so if you are really interested in it, so you have to learn it. Each software by software, you have to learn it. Okay. Now what the next thing is, now the next thing is I have created one hardware. I have created one application. Now suppose I have a board here. Okay, so I will connect that board to my laptop. Okay, just to click here, Xilinx tool, program FPGA. Click program. Okay, so when I click the program, what will happen is the binary will be downloaded to FPGA. What is this binary? Binary of the hardware. Hardware will be created in this side of FPGA. So hardware is created. Now, after that, you have to run this program by clicking this application I have created, right? Right click it somewhere here, run as launch on hardware. Okay, this will run. And you will show the output screen. You can give the input there, get the output there. This is an encryption, so you can give input like some text. You will get the output. Okay. Establish the that you can. You can first of all you can get the latency from here. How much latency it is taking, it will come here. You can check how many clock cycles you are taking and compute the performance. Second method is you can write C code here to calculate how much time it is taking. We can start a timer. There is one function for that, start timer. Then I will execute my encryption, stop timer, check the time. Usually more, it won't show that much accuracy, that C function. It's better to get it from here. Calculate it by yourself. How much latency? This latency is correct. calculate by yourself how much latency it is taking, calculate it, how much time it is taking. Okay, you can see the performance. Performance of my design. The normal execution means instead of C program, you can use timer, how much time it is taking. It will be nanoseconds actually. Yeah. I'm not getting that. Here, I cannot execute since I don't have the board, sir. So I cannot show it. Minimum, maximum? Yes, sir. Minimum, maximum, what minimum, maximum? Can you elaborate your question, sir? What exactly you want to see? Yeah, that's what I have shown here. This one, right, sir? This one. This one is the latency of the entire encryption process. This is in nanosecond. Okay. So this is with the, say here time you can see nanosecond, right? So this is the latency. One clock cycle is, it will runs in nanosecond and it is taking 1405 clock cycles. Okay. This is without any pipelining or parallelism or anything. If you introduce pipelining and parallelism, this will reduce to around 140, 200. This 1000 will reduce to 140 or 200. When I was doing, it was around 220 or something like that. That I will tell. So till here, it's okay, right? Yeah.
What is a Verilog file and who creates it?
Like I specified, right? So here I have written in C. Then what I have done, I have packed it as an IP, export RTL. That means that time it will convert to this Verilog code. Here you can see the same Verilog code. This tool will convert it into Verilog code.
In logic encryption, will the logic gates be placed randomly for each prototype or product? Also, if the keys are also random.
Keys are not random. Key gates are random. We are placing it in random location. Number of key gates are random. Okay, but the bits, they are not random. See here, see in the logic locking technique, if I am giving random keys, it won't work. See, for XOR, here output is coming from G5. Okay, it will be an 1 or 0. The same output should go here. Okay, so what input should I give to this key input so that the same output will go there? Okay, that kind of input, that input is the key input. Okay, if I give the wrong one, this gate will do XOR of the two and something 0 or 1 randomly it will give. Okay. Okay. Random means random for one design. It won't change after that. Okay, that key bit will decide based on the input and output. Okay, it won't change after the design. Okay, so after this, time is almost over. I wanted to tell you one more. Anything else? That's what I was telling, sir. Hardware accelerator. So cryptographic accelerator is the hardware security we are providing through hardware. Okay, accelerator. If you want to give security for my hardware, what you should do? You have to go for any one of the technical, like logic locking. So what I have to do if I want to go for security of my design, this is my design. This is the AES my design. Where is the security? I have to add the key gates. For that, you can do two ways. You can go to the C language and you can add appropriately if you clearly know it. Because if you are keeping an if or while loop, what hardware it is producing, based on that you can analyze and you can do it in C itself. That is one method, high level insertion. Okay, second method is you have to go here. Okay, here we have we have Verilog code. You have to do it here. Okay, usually logic locking is little bit difficult for software people, but still you can do it in high level. But I'm not telling it will give the correct method. Okay, you can try. The thing is, logic locking is an emerging thing. It is applied only to integrated circuit security. Okay, but still you can go for FPGA. Some work has been done. You can go do it in either high level coding or in Verilog coding. No. Coding development, if you are doing it, we won't be able to check the functionality properly. First, we have to do the design, check the functionality, then you have to add. Usually, if you are coming here, we will add after synthesis. Okay. Now, who is doing? Researchers are doing. After some time, it will be integrated to the software. Access control in the sense. That you can go for both hardware and software-based solution. First of all, you have to create a hardware for that. Nowadays, how they are doing access control is they are keeping a small hardware firewall in it. Okay, hardware firewall, then giving access permission only to the authorized user. Okay, then creating software for that. Nowadays, FPGA access control is being done by like that. So if I am going for hardware-based firewall, almost all the servers are having hardware-based firewall. So we don't have to spend resource or our effort or for that. It's already there. We can use that. Okay. So this law, then one more thing what I want to tell you is, so if you want to improve the throughput or reduce the latency, you can go for pipelining, right? Function pipelining, loop pipelining, or operation pipelining. Okay, so two ways are there. If you are very much same thing, very much familiar with the Verilog, you can do it in Verilog. Otherwise, go here. Here in right hand side, you can see some loop and all, right? You have learned it in compilers, right? Optimization, loop unrolling, pipelining also. So just to go to anywhere you can use pipelining and parallelism, depends on your knowledge actually. A loop I'm taking, right click, insert directive. Okay, here pipeline you can see, or loop unrolling. Loop unrolling and give you. Okay, click OK. So on Pragma, I will come here. Okay, Pragma, HLS unroll. So what will happen is it will be converted to the particular Verilog code, and here loop unrolling will happen. Okay, like that you can do it. This is what the software based. This we cannot tell we have done that. Software is doing that. You can improve the performance of the design. Okay, so once you get familiarized with all these hardware thing, you can go for implementing security in FPGA. How? The same way, whatever the security measure. Suppose if you want a secure memory, what is a secure memory? I mean, how security is providing to memory usually through software means through access control, right? Then we have something in CPU, like we will give some permission to some pages and all those things are there. How we can do it in FPGA? You can write the code just like this one, either in C or in Verilog. Okay, so we have We have all the components here. Where is that component? Okay, which are all, if you have a logic regarding security, you can create your logic here and to make one particular memory inaccessible to outside world. That way you can give security. On example, I'm telling. Okay. So here I have not shown the memory things. Memory are there. SRAM is there. Static RAM is there. DRAM is there. Block RAM. Those are all things inside FPGA that you can read it in a book. So whatever the security measures you want to take, you can keep it here. And logic locking eliminates almost all attacks. Reverse engineering, not possible if we do logic locking without the proper key. Okay. Then side channel attack. After logic locking, if we analyze the site power and all, additional gates we have already placed. So an attacker may not able to know the correct thing. Okay. Then which is there, insertion of Trojan. If the attacker doesn't know the key bits, he will not know the logic of the circuit because we have kept so many gates. He don't know the logic of the gate. And he don't know where to keep the Trojan. He don't know where to keep whether the trigger will activate the Trojan or not, because on trigger circuit will be there. In between our additional gate will be there. Key is there. So his trigger may or may not work. Okay. So almost all hardware level things can be avoided by logic locking. The only challenge in logic locking is writing code for logic locking. Okay. So this is an overall view. So do you have any doubt? I'm not getting, sir. Mobile. Inside, I see this logic locking is in research only. Which one? So that's what I'm telling. Logic locking is in only in the research place. Reverse engineering. I'll take the slides, sir. One second. Where is that? Yeah, here. Yeah, yes, sir. What difficult, sir? Nothing is difficult here. You cannot. Sir, that is iPhone privacy matter. How will I know? See, iPhone has not told anyone that they are using an SoC. Okay, that itself they are not telling the outside world. The entire iPhone is not made of FPGA, sir. I'm just telling that there is a part inside to improve that. Nowadays, iPhone is coming with AI, right, sir? Those things they are executing inside FPGA. That's what I told. Yeah.
What are the performance parameters used to measure security?
Security performance measures, if you are considered, that depends on what you're taking. If you're taking an algorithm, what are the security parameters you have to take? So suppose if I am using are you talking about algorithm? Security parameters. So if you are taking, suppose an encryption algorithm, Performance, but not security parameters. Okay, performance parameters are latency, frequency. From these two things, you can able to calculate the performance. Latency and how much, what is the frequency? Here it is running in 100 megahertz. It's here in here. Okay, 10 timing 10 nanosecond means it's 100 megahertz. Okay, so through latency and this frequency, you can calculate throughput. Number of clock cycles divided by that timing. And efficiency, again, you have to know if you want to calculate the efficiency, you have to go for how much utilization it is taking. Okay. Performance and efficiency. Yeah. Yeah, this is called a cryptographic accelerator. Okay. Mm. No. Yeah. Mm. Mm. Not only HLS, you have to go till Vivado. SDK is not necessary. SDK is just application. You have to go till Vivado. Anything else? Okay, thank you all.